36 seconds after Apollo 12 lifted off from Cape Kennedy, the rocket made its own lightning. The Saturn V and its exhaust plume formed a conducting column nearly a mile long, connecting a charged sky to the ground, and the discharge ran straight down through the spacecraft carrying 3 men. 16 seconds later it happened again. Every warning light on the command module panel came on at once, the guidance platform tumbled, and in mission control the telemetry stream that gave Houston its only window into the vehicle turned into meaningless noise. The fix came from one flight controller who recognized the pattern of that noise from a test he had watched a year earlier, and it involved a switch that the flight director had never heard of. Apollo 12 launched on November 14, 1969, 4 months after Neil Armstrong stepped onto the Sea of Tranquility. The crew was Pete Conrad, Dick Gordon, and Alan Bean, all Navy men, all flying together for the first time as a crew on a lunar mission. President Richard Nixon had come to watch in person, the first sitting president to attend a crewed American launch. The weather that morning was poor by any ordinary standard: low cloud, steady rain, a cold front moving through, but the launch rules of the time addressed thunderstorms and visible lightning, and there were none in the area. Nobody at Kennedy Space Center was worried about a storm, because there wasn't one. The countdown went clean. Conrad, in the commander's seat, later said the ride felt normal for the first half minute, which it was. The Saturn V rose through the overcast and disappeared from view within seconds of clearing the tower, which is why the film of that launch shows the vehicle vanishing into gray so quickly. Then, inside the cabin, there was a flash bright enough to see through the small windows, and the master alarm sounded. What Conrad, Gordon, and Bean were looking at made no sense as a single failure. All 3 fuel cells had dropped offline, the main buses had disconnected. The spacecraft was running on its entry batteries, which held a limited charge and were meant for the last minutes of the flight, not the first. The caution and warning panel showed so many faults simultaneously that no fault could be isolated. Conrad's transmission to Houston was blunt and slightly amused, reporting that they had just lost the platform and that everything in the world had dropped out at once. He asked Houston what they saw. Houston saw nothing usable. The telemetry from the command module, hundreds of measurements per second describing pressures, currents, temperatures, and voltages, had gone to garbage, not blank, which would have been simple to interpret. Garbage. Numbers moving in ways that corresponded to no physical state a spacecraft can occupy. Rows of data on the flight controller's consoles filled with values that were internally contradictory. A controller's job in that moment is to distinguish an instrumentation failure from a real failure, and that distinction had just been erased. At the flight director's console sat Jerry Griffin. It was his first launch in that chair. He had a vehicle climbing at several thousand feet per second, a crew reporting total electrical chaos, and a data stream telling him nothing. The abort decision belonged to him, and it belonged to him within seconds, because the escape tower on top of the stack would be jettisoned shortly after the first stage burned out. After that, the abort options got worse. Griffin pulled his controllers. Around the room, the answers came back in variations of the same thing: no data, unable to assess. The systems specialists could not confirm whether the spacecraft was dying or whether its instruments were simply lying. One voice did not say no data. John Aaron was the ECOM, the controller responsible for the command module's electrical, environmental, and consumable systems. He was still in his 20s. He was looking at the same corrupted numbers as everyone else, but he had seen that specific corruption before, and almost nobody else in the building had, because it had happened once during a test, and it had happened when he happened to be watching. Roughly a year earlier, during a test at the Cape, Aaron had seen the telemetry from a spacecraft go strange in exactly this way. It was not a mission, there was no crew aboard. The data had briefly turned into a mess of impossible values and then recovered, and the test had continued. Most people forgot it. Aaron did not forget it. On his own initiative, he went and found out what had caused it. The answer took him into a box of hardware that flight controllers rarely thought about, called the signal conditioning equipment. The signal conditioning equipment does an unglamorous job. Sensors all over the spacecraft produce raw electrical signals in whatever form the sensor produces, and those signals are useless to the telemetry system until something converts them into standardized voltages that can be sampled, encoded, and transmitted to the ground. That is what the SCE does. When it works, nobody thinks about it. When it loses its normal power supply, it stops converting properly, and every measurement passing through it becomes nonsense at the same instant, regardless of whether the underlying system is healthy. And the SCE had an auxiliary setting, a backup mode designed to keep it running on reduced voltage. Aaron had learned that a year before, for no reason other than that a strange thing had happened and he wanted to know why. Now the pattern was on his screen again, and he understood in a few seconds what the rest of the room was still trying to diagnose. The spacecraft might be fine. The instrument that described the spacecraft was starving. He called it to Griffin. Try SCE to auxiliary. Griffin had never heard of the SCE. The call meant nothing to him as a system, and he had a stack of other problems, and the man making the call was one of the youngest controllers on the floor. He passed it to the capsule communicator anyway. That decision, made under time pressure and without understanding, is one of the reasons the flight worked. Gerald Carr, the CAPCOM, read it up to the crew. Apollo 12, Houston, try SCE to auxiliary. On board, Conrad heard the call and did not recognize the acronym either. His response, recorded on the air-to-ground loop, was closer to bafflement than to acknowledgement. He asked what that was, out loud, on the way to orbit, while riding a rocket that was still accelerating. Alan Bean knew. The switch sat on a panel on the lunar module pilot's side of the cabin, and Bean had encountered it in training, in a simulation, once. He reached over and moved it. The telemetry came back. That single switch throw did not fix anything about the electrical system. It fixed the ability to see the electrical system, which was the precondition for fixing anything else. With real data on the consoles, Aaron could look at the fuel cells and confirm they had not failed, they had disconnected. The lightning had produced a voltage transient large enough to trip the overload protection that ties the fuel cells to the main buses. The cells themselves were healthy and sitting there producing power that was going nowhere. Aaron walked the crew through reconnecting them, one at a time, and the spacecraft came back onto its normal power supply, while still under boost. All of that happened during the climb to orbit, and none of it touched the rocket. The Saturn V had its own guidance system, housed in a ring called the instrument unit, mounted below the third stage and entirely separate from the command module. The lightning had knocked the spacecraft's inertial platform off its alignment, so the crew's own navigation reference was useless, but the launch vehicle never wavered. It flew the ascent as programmed and put Apollo 12 into an orbit within a fraction of a degree of the intended one. The men in the spacecraft were passengers on a machine that had not noticed the problem. Once in orbit, the immediate emergency was over, and the harder question opened up. The crew realigned the inertial platform by sighting on stars, standard procedure, no drama. The instrument readings all checked out. Systems tests over the next hour and a half found nothing broken, but a lightning strike is not a discrete event with a known blast radius. Current had passed through the length of the vehicle, and there was no way to know from inside what it had done to circuits that were not powered at the time and would not be powered for another 10 days. That is where the parachutes came in. The command module's 3 main parachutes are deployed by pyrotechnic devices, small explosive charges fired by electrical circuits at the end of the flight, during re-entry. They are single-use. There is no way to test them without expending them. Engineers on the ground worked the problem for hours, and the concern was concrete. A current surge could have degraded those circuits or the initiators themselves in a way that would show up only at the moment the crew needed them, roughly 400,000 feet above the Pacific, with no backup. There was no test, there was no inspection, there was no instrument reading that would answer the question. What settled it was a piece of logic rather than a piece of data. If the pyrotechnic circuits had been damaged, they would fail on re-entry whether Apollo 12 came home immediately or came home after landing on the moon. Aborting the lunar mission would not make the parachutes safer, it would only trade a moon landing for nothing. The mission continued, and everyone involved understood that the crew was committed to a re-entry whose ending could not be verified in advance. Conrad, Gordon, and Bean flew onto the moon carrying that. 4 days later, Intrepid separated from Yankee Clipper and descended toward the ocean of storms, and Apollo 12 did the thing it had actually been designed to do. Apollo 11 had landed long, well past its target, and NASA needed to know whether it could put a lunar module at a chosen point rather than in a general region, because everything afterward, the geology, the traverses, the site selection, depended on precision. Conrad flew Intrepid down into a crater rim and set it beside Surveyor 3, an unmanned probe that had landed in April 1967 and had been sitting on the lunar surface for 2.5 years. The distance between them was close enough to walk. It remains one of the most precise pieces of piloting in the program, and it settled the question of whether a lunar module could be aimed. Conrad went down the ladder first. He was a short man, and his first words on the surface were a joke about the difference between his own height and Armstrong's, which he had reportedly bet a journalist he would say, to prove that NASA was not scripting the crew's lines. He collected the bet later and said the payment never arrived. The moonwalks produced almost no television. Bean, setting up the color camera on the surface, swung it across the sun, and the sensitive tube inside burned out permanently within minutes. He tried tapping it with a hammer. Nothing brought it back. 2 lunar surface excursions, more than 7 hours outside, and the entire visual record is still photography and voice. Conrad and Bean walked to Surveyor 3, cut pieces off it, including its television camera, and brought them back to Earth for engineers who wanted to know what 2.5 years of vacuum, radiation, and temperature swings do to hardware. Those parts came home in a bag. Then came re-entry. On November 24, 1969, Yankee Clipper hit the atmosphere over the Pacific with 3 men aboard and one unanswerable question in the circuitry. The drogues came out, the mains came out, all 3 canopies inflated. The pyrotechnics that had been sitting in doubt for 10 days fired exactly as designed, and the only injury of the entire flight happened after splashdown, when the capsule hit the water hard and a camera broke loose from its mount and struck Bean in the head, opening a cut that needed stitches. He had ridden through a lightning strike, a lunar landing, and a re-entry, and he was hurt by a camera in the last 5 seconds. The investigation afterward established what had happened at 36 seconds and again at 52. There had been no thunderstorm. The atmosphere held enough of an electric field, and the Saturn V, with its long trail of hot ionized exhaust, provided a conductive path that would not otherwise have existed. The vehicle triggered a discharge that the sky was not going to produce on its own. The rocket built the lightning rod, and then it built the lightning. That finding rewrote the launch rules. Weather criteria for American launches stopped being about visible storms and started being about the electrical state of the atmosphere itself, including conditions that look harmless to an observer on the ground. The specific cloud types, field strengths, and standoff distances have been revised many times since, but the principle that a launch vehicle can create its own strike in benign-looking weather traces directly back to what happened over Florida that morning. John Aaron went back to his console. 5 months later, he was on the floor for Apollo 13, and when the crew had to bring a nearly dead command module back to life on a power budget that left no margin for error, Aaron was the one who wrote the power-up sequence, item by item, deciding what could be switched on and in what order and what would have to stay dark. The nickname that followed him inside the agency, the steely-eyed missile man, came out of those 2 flights. The switch itself is worth remembering for what it says about how that program actually worked. No procedure existed for the situation Apollo 12 was in. The correct action was not in a checklist, not in a flight rule, and not in the training curriculum. It survived in exactly 2 places: in the memory of a young controller who had chased down an anomaly nobody assigned him to investigate, and in the memory of an astronaut who had seen the switch once in a simulator and could find it by feel while pulling several Gs. Apollo 12 proved a lunar module could be flown to a chosen spot on the moon, and that precision made every later mission's science possible, from the Fra Mauro Highlands to the valley at Torres Litro. It also changed how every American rocket since has been cleared for launch, because the atmosphere no longer has to be threatening to be dangerous. 3 men rode through 2 lightning strikes and came home because 1 man on the ground had been curious about a data glitch that had nothing to do with him. If you want more stories from the era when a program this large ran on that kind of memory, subscribe and tell me which single decision in the Apollo program you think came closest to going the other way.